Fibonacci numbers efficiently. Yeah. And we compare three methods. The first two for the regular part. The last one I didn't talk about in class, but it is given in our textbook. It is very interesting, so I include it as an option for extra credit. Later, I will explain, not today. Yeah, today, I only explain the regular part. Yeah. Next time, after the Thanksgiving break, I will find time to explain the option, the last option, that one. Yeah, because I need at least a half an hour to explain that option. Today, I need approximately half an hour. And after the break, we need another half an hour to explain extra credit part. Yeah. All right. The first two algorithms given in our notes, pretty simple. Yeah. The implementation, we know the Fibonacci number, the implementation, just a simple addition, right? Yeah. F sub n equals F sub n minus 1 plus F sub n minus 2. This simple formula, we use two different ways to implement. Whatever you do the implementation, it is very simple, right? Yes, too simple. Yeah. From that point of view, your programming part for these two algorithms, actually, you can do very fast. Yeah. So then that's the reason I like to add a little more requirements. Otherwise, this project too simple, right? Yeah. First, I do not like to make the project too hard. Yeah, because already near the final stage period, you have a lot of work. So I do not want to make it too hard, but at the same time, I like you to learn something interesting. Yeah, not make it too simple. Yeah. So with this project, you can learn something useful for your computing knowledge. Yeah. All right. The first one, recursion directly. Straightforward algorithm. Here, I give you the reference in our notes. Yeah. When you call it, use the recursion way. So if you use the iterative way, it will be very fast. Here, I use this example to let you feel about where you use the recursion without considering redundant calculation, it could be very slow. So that point, I want you to feel about it in the algorithm number 1. Yeah. Because you will feel it is very slow. It is very slow. Yeah. How slow it is. Yeah. So here I give you some idea how slow it is. Yeah. All right. Yeah. Here I'm talking about algorithm number 1. All right. Based on the requirements, here I use the 30 seconds computation time. 30 seconds, that's quite long, right? 30 seconds. Using 30 seconds, you can calculate how large the Fibonacci number you can calculate. Yeah. So based on my experience, because we know different students use the computers with different calculation power, right? Different computation power. So, so your number will be slightly different. Yeah. But here, I just give you the, approximate one. That is F of 45. How about that? So when you calculate Fibonacci number 45, that should not be a too big number, right? F45, you need to use 30 seconds. How slow it is. That's too slow, right? Think about that. Yeah. Because later you will see in the later description, I will ask you to calculate how large it is, the Fibonacci number. Later I will ask you to calculate Fibonacci number of 10,000. Look at that number. 10,000 here and 45 at the beginning. How much is the difference? 10,000. Think about that. But 10,000, you will see the computation time, really fast. Really fast. You will see the response time, less than 1 second. Think about that. Less than 1 second. And there, 30 seconds, only F45. Huge difference, right? Yeah. So that's something I like you to feel about it. The huge difference between two different algorithms. So that's one thing. But the second thing is, this one we need to consider overflow problem. Our item number 2, we have overflow problem. Yeah. In our project 1, we avoid overflow problem. In our project 1, remember, I set the range for the coefficients. Actually, the coefficient part, not that important. The range for our variable x value between 0 and 1. In that way, we can control the range of the polynomial. It will be in the, good range. Yeah. So we don't worry about the overflow issue. But this one, we cannot. We cannot. Because the Fibonacci number, first, it's an integer, positive integer, when n relatively large. Second, we know integer has some upper bound. So if you pass the upper bound, you will have some overflow. When overflow occurs, what you should do? Yeah. And in the item number 3, yeah, so we use Java big integer class. So here you can have a chance to use Java big integer class. This one you can avoid the overflow problem. Yeah, because when you use Java integer, you will never get an overflow. Yeah. That's the reason I ask you to calculate f of 10,000. Otherwise, how can you calculate f of 10,000 sub 10,000? Already, because that's a huge integer. Yeah. But now you can calculate with Java big integer class. You can calculate, as a piece of cake. Yeah. All right. So the overflow problem. Yeah. You can overcome it, but next thing, I need to help you understand this overflow a little more. So item number 2, you not just get around overflow. But item number 3, we find a way to get around overflow. But if you get around it, you do not understand it, right? Yeah. So the item number 2, I designed it to make you understand overflow. Yeah. Okay. Understand overflow. Yeah. So I ask you to use two methods to calculate that overflow bound. There is a bound, F sub n max. That's the one right before the overflow. If you go to the next one, for example, if you go to F n max plus 1, just the next Fibonacci number, you get overflow. Okay, yeah. What is that n max number? N max number. Yeah. You know, based on my experience before, as I remember, n max around 92 or 93. Yeah. Just approximately. Yeah. So you will check it. Yeah. 92 or 93. Yeah. In that close to that. Yeah. But here we use two methods to calculate, to find that number. When you find it, when you work on it, you will understand the overflow better. Okay, all right. So let me move to my PowerPoint slides to explain the overflow problem. Yeah. Oh, yeah. So let me just go to the very beginning. Yeah, this one. C.0, very beginning. All right. Okay. All right. Explain overflow in project 2. Yeah. All right. Yeah. So first, for that overflow, yeah. Here I assume we use Java. Okay. Yeah. Because for C++, I do not know that information. Yeah. C++, yeah. But here, let me just use the Java to talk about this concept. Yeah. In Java, so we consider the overflow problem. All right. It relies on the data type we are using, right? The data type we are using. Yeah. We want to use a data type, integer data type, as large as possible. Okay, yeah. Here, you may like to consider the long integer, but for the long integer, there are two types. One is the long directly. If you use long directly, that is signed positive, negative, right? Yeah, because long directly, you can represent negative big integer, so the signed one. But another version, unsigned. If you use unsigned long integer, then you do not need to represent the negative side, so you can represent larger long integer. We know the long integer, we use 64 bits. So that is 8 bytes. 8 bytes, yeah. In Java, you can, you may feel already big enough, right? Yeah, how large it is. For signed, approximately 1/2 you represent positive side, 1/2 you represent negative, because the first bit 1, yeah. How do you represent sign? in long integer. Use first bit. First bit we call the sign bit. First bit is the sign bit. All right. So for the sign bit, 0 means positive. All right. 1 means negative sign. Okay. Positive including 0. Okay. Yeah. Including 0. You know it. All right. Yeah. Sign bit. Then the largest integer you can long integer you can represent 2 to the 63 minus 1. Because 63, because you can only use 63 bits. The first bit you cannot use. That's the sign bit. So you cannot use it to represent the number. Yeah. So that's approximately, yeah, we did a calculation 9.2 times 10 to the 18th power. 18. Is that big? You know, it depends on, you know, how do you want to use it? Okay. When we use it to calculate Fibonacci number, that's not big enough, right? That's not big enough. Yeah. All right. Unsigned long integer, that's all the bits, because you do not need to represent the sign bit, right? Yeah. No sign. Yeah. All numbers, all bits can be used to represent a number. So the largest you can use to represent 2 to the 64th power minus 1, approximately equal to 1.84 times 10 to the 19th power. Okay, yeah. All right. After that, you will get overflow. Okay, yeah. So there is a bound like this. After, yeah, let's say, after your Fibonacci number f of m, if it is greater than, let me use this long integer max. Okay, so here I do not specify which one. Yeah, depends on in your program which data type you want to use, long or unsigned long. Yeah, yeah. In this program you can use either one. Okay, yeah. So I do not require which version you use. Yeah. So you choose by yourself. Yeah. So I use this L sub max to represent when f sub n greater than this L max, overflow occurs. Okay? Yeah. All right. Okay? Yeah. Now we need to discuss when overflow occurs, what would happen? Okay, the first question. Okay? Question. When the overflow occurs, what do we see? What do we see? An error, sorry, an error message, no. The answer is no. No error message. Okay? No error message. You just see some number produced. If you print it out, you see some number, but nobody tells you there is overflow. Happen behind the scene. Nobody tells you that. you do not even realize you may get an overflow. Okay, yeah. So no error message, no special thing, no special sign, warning, alert, nothing. Then the question, how do you know you hit an overflow? Right? How do you know there is an overflow? That question is important. Otherwise, if you do not answer this question, otherwise you will produce garbage. The Fibonacci number you compute is wrong, you produce garbage. All right? No warning sign, but you produce something completely wrong. Yeah. Why it is wrong? So yeah, let me explain why garbage. Yeah. My writing a little slow. A little slow. Okay. Why garbage? All right. Because, yeah, let me use this simple diagram. Oh, yeah. Simple diagram to explain that. I use this to represent 64 bits. All right. Then, when you do calculation, yeah, sooner or later, we get an overflow. Overflow, what do you mean overflow? You need more bits to represent correct number, right? In order to represent correct number, you need more than 64 bits. All right. So here we imagine the correct number if we can extend our representation bits. We can, represent correct number, but now there is no this part. That's the imaginary part. Yeah. So when overflow occurs, if an overflow occurs, or sorry. All right, this part truncated. That imaginary part will be truncated. Okay, truncated, but the computer does not tell you there is a truncation happen behind the scene. So you do not know it. It is truncated, but you still see a number produced, right? The number just use the last 64 bits. Number produced. Okay, so that's a garbage number, right? It's truncated. Incorrect. Okay, if you use it, it's incorrect. All right, yeah. And something very strange. Yeah, here I can tell you, yeah, because when you do experiment, you will see something, strange or weird. Yeah, what kind of strange? So here, I tell you the problem. So when you see it, you can understand immediately something very strange. All right, here I assume, so here, suppose you use signed long, all right? So you just use long. Yeah, if you use long, yeah, not unsigned. Unsigned because you won't see signed thing. Use long, we know it's signed long, right? Yeah. There is a sign, okay? If you use sign law, you will, when you produce that number, you will see negative number. Yeah, you will see, yeah, let me just write negative number produced. Produced. Yeah, why negative number? That's simple. Because after truncation, this position could be 1, right? The highest position bit could be 1. We know 1 is the sign bit. When highest position bit is 1, sign bit, then that number becomes negative. So then you feel it's ridiculous. How can you make a Fibonacci number a negative number? Right? So that's wrong. So from that one, you can see it's a wrong number. Otherwise, you won't see it's a wrong number. Okay. So when you do the calculation, yeah, big, after 92, 93, yeah, usually when you pass that 92, 93, if you use the long integer, you will see you may have a negative number, negative answer. So that is wrong. That must be wrong. All right. Yeah. Okay. Yeah. So that is the story behind the overflow. Okay. All right. Next, after you understand this background, next we need to look at the detection. So that's why my method 1, method 2, I designed those 2 methods for overflow detection. Two methods. All right. Method 1, use the Fibonacci formula. All right. Yeah. Method 2, use the overflow property. In this way, you have another chance to understand the overflow phenomenon better. Okay, all right. So here, let me give you these 2 methods, the description of these 2 methods. All right. Yeah, today I will use much more than 30 minutes. Yeah, let me just complete the whole thing. Yeah. Yeah, otherwise, if I come back next time, you may forget, the first half of the story. Yeah, let me just complete the whole story together today. All right. The Fibonacci formula, we know it, right? Yeah. 1/√5, the golden ratio phi to the n minus -1 to the nth over phi to the nth. All right. Yeah. Now let us estimate that f and max. Yeah. Just the good Fibonacci number right before the overflow limit. Okay. Yeah. So we require less than capital L max. All right. Yeah. Now we do some math computation. Yeah. Here, there is a negative sign. All right. There is a negative sign. -1, positive, negative, alternative sign change in, alternatively, right? And another thing is the denominator has that phi to the n. That makes the computation a little more complicated. So we need to find a way to simplify the formula. Yeah. So let us simplify it. All right. So here we take absolute value. We know Fibonacci number is positive, right? Yeah, the reason here I use absolute value is because in this expression, there is a negative term. If I use absolute value, so I can, get around, I can take care of that negative term. Yeah. Less than 1 over root 5 phi to the m plus 1 over root 5 times 1 over phi to the m. How about that? How about that? Okay, yeah. I make the Fibonacci number expression a little larger, right? Yeah. I make it, plus sign the second term all the time. I never consider the negative case. So I make the Fibonacci, I make the upper bound for the Fibonacci number, right? Then I like to, make this larger representation less than L max to find that n, to estimate that n. Yeah. But you may feel this kind of estimate may not be accurate, right? May not be accurate. I will let you know this kind of estimate is very accurate, extremely accurate. Here, I try to convince you, right? I try to convince you why this kind of generous enlargement still make it extremely accurate. Yeah, let me try to convince you. All right, here, look at this term. How large is this? How large is it? All right, yeah. Remember, at the beginning, I give you some idea, the overflow place where n equals 93, right? Approximately 93, yeah. That's what I did before, yeah. And approximately, 93. Yeah. Here, let me calculate. When n equals 93, let us calculate this number. All right, this number, yeah, approximately, yeah, some number I forgot, yeah. So let me check it because before the class I used the Wolfram alpha. I did a calculation, yeah. I did a calculation below, yeah. So, all right, so here, look at that. 1.64 times 10 to the negative 20th. Yeah. Yeah, let's go back. Let's continue this one. All right. So all right, sorry. I need to change the color again. Yeah. Not very smart. Yeah, the software, not very smart. 1.64 times 10 to the negative 20. Do you know how small this number is? Negative 20th. How small it is? Yeah, so let me tell you. In computer, you cannot represent a floating point number accurately, right? Because a computer has limited number of digits after the decimal. At some point, you have to truncate it. to represent a floating point number. Yeah. Floating point number, there is a rounding error for computer. For any computer, there is some rounding error. That rounding error in some range, 10 to the, negative 12 something, right? 12, 10 to the negative, 14, in that range. Yeah. 10 to the negative 12. You can see this number, this last term already much, much smaller than the rounding error of the computer. Your computer error is larger than this one. Think about that. Your computer rounding error is much, much larger than this one. Can we ignore this term? Because much, much smaller than the rounding error. All right? Yeah. So then that means we can do the calculation less than L max. How about that? After we cross out the second term, relatively complicate the second term, we know it is so small. We are pretty safe to erase it, right? Yeah. Then we feed to the n less than √5 times L max. All right. Take natural log. We can take natural log, right? And natural log phi less than natural log of √5 times capital L max. All right. Then we have the inequality n less than natural log of √5 L max over natural log of phi. Can you calculate this expression? This expression will give us the n max. Yeah. How about this? At the end, we can represent n max equals floor function of that natural log √5 L max over natural log of phi floor function. How about that? Okay, how about that? Right? This is our method 1 to calculate the overflow. Method 1. Okay, all right. Method 2, use the overflow property. Overflow property. All right, yeah. Here I do not have the space, yeah, because my next slide will be, our hashing thing part, yeah. Yeah. So I need a little more space to talk about method 2. Yeah. All right. Okay. Yeah. I can go back here to talk about method 2. How about that? Yeah. Here I have a lot of space. Yeah. Method 2 detection. We know use the overflow property. All right. Yeah. It's very simple. Yeah. Very simple property. All right. Yeah. Well, we know when we calculate Fibonacci number, we do addition, right? A equals B plus C addition. Yeah. All right. When we do addition, an overflow could occur. Yeah. All right. So here, our goal, overflow detection. Yeah. Because there is no special warning, special sign. Yeah. You may make argument that negative sign, right? But sometimes you can see that negative sign, sometimes you cannot. Okay, so that may not be reliable. Think about if you use here, if we use unsigned long, unsigned, you never see that negative sign, right? Long. Let's assume if we use unsigned long, you never have that negative sign. All right, yeah. So here, two cases we need to consider. The first case, no overflow. All right, now first case. Second case, overflow case. And their behavior is different. So we use the different behaviors for these two cases to do the detection. Yeah. So what kind of behavior? Yeah. All right. No overflow. Yeah. When no overflow, if you compare A minus B, it will equal C, right? Yeah. A equals B plus C, then you do this change. A minus B, this will be equal. All right, yeah. But for the overflow case, all right, so now you do, because you calculate B plus C, you get a number, let me call A0, all right? Because that number may not be equal to A. May not be equal to A due to the truncation. There is a truncation, right? Yeah. May not be, so you basically you get A0, all right? Truncated, a few bits at the beginning could be truncated. Then you check, after that you check A0 minus B won't be equal to C. After that, you compare A0 minus that B, compare with C won't be equal. If you see equal, then you know no overflow. Okay, all right. If you check not equal to C, you can make your conclusion and overflow occurs. Okay, yeah. Then the previous one, yeah, because overflow occurs, that means the current M is not good, right? The current, because when you choose some N, the current M is not good. Okay, yeah. The previous one, is N max. Okay, so you find that N max. Yeah. After you hit the first overflow, you stop, right? Hit first flow, you stop. Yeah, but you use that previous good N as the N max. Yeah. After that, you use two ways to find N max. You compare these two N max and see if they are the same. All right. Yeah. If not the same, so you have some mistake somewhere. You need to fix it. Yeah. If you use two different methods to get the same answer, then it should be correct. All right. Yeah. Or we can say it is very, very likely the percentage it is correct, very high, right? We verify it. Yeah. All right. So that's the whole story about the overflow, and you use this background knowledge for that option number 2. Okay. Yeah. It's non-trivial. Yeah. So that's why I spend a lot of time. Yeah, I spend, yeah, let me see, more than 40 minutes, 45 minutes, approximately 45 minutes to explain this important phenomena. Yeah. But with this experience, I think you will be better. You know, when you go to the computing industry, you have this background. Yeah, that's very useful. All right. Yeah. All right. Any question for this particular problem? Yeah. All right. Yeah. So we do not have much time, but we can do a short introduction. Yeah. And then the remaining part we will do next time. Yeah. All right. So let me move to C.1. Why using hashing? So here I talk about the hashing technology. Background, still background a little bit. Yeah. You may heard of this term a lot in your real world life experience, but here we need to learn the ideas behind the algorithm. Yeah. First, this method is very useful, yeah, but we like to know a little more about the algorithm detail for this important, algorithm. Yeah. Why using hashing? Okay. Yeah. How to find data item in a given with a given key. So that's the question. Right. All right. So this question, is it a search problem? If we recall, this is a search problem. Given a key, find item with this key, containing this key. That's the search problem, right? Yeah. For the search problem, so let's review a little bit. We have learned a linear search and a binary search, right? Other than linear search, binary search, what else? Not many, right? In this class, yeah, that's all we learn. Those two usual common search algorithms. Yeah. Here, another one, hashing, another search algorithm. Yeah. Given a collection of data dynamically, here you can see in the typical real world situation, data comes in dynamically, keeps coming and keeps going, come and go frequently. So your data changes dynamically. All right. Yeah. So here we assume that's the typical situation we consider in our real world applications. Yeah. All right. Each data item is identified with a unique key. Yeah. That's important. Yeah. In order to find the right data item, we need some key. Okay. Yeah. That's okay. Yeah. So we have to do that part. Yeah. Otherwise, you cannot identify different data pieces. Yeah. So that's a normal requirement. Okay. Yeah. The question, how to make your data search efficiently? General question, right? Yeah. So here, your background, you have linear search and a binary search. The linear search, we know. So here, let's recall a little bit. Linear search, binary search. The binary search, we know the data must be ordered, right? Yep. We have to sort the data based on the given key. Okay. Then you can apply binary search. Before you sort it, you cannot apply binary search. Yeah. But we know for the linear search, the efficiency bigger of n, the binary search bigger of log n. That's what we have so far. Yeah. The next question. Yeah. So now, when we try to find a new search algorithm, yeah, some people may not feel happy about linear search, binary search. So they want to find a new search algorithm that performs better than linear search, binary search. Okay, so that's the reason. That's the motivation behind this new algorithm. Yeah. So let's see. Yeah. In order to do better, the designer. Yeah. So here, the designer need to consider a new data structure. Probably is needed. New data structure for a new algorithm, non-trivial or advanced. People may need to develop some new data structure. Okay, yeah. So here we need that. We need a new data structure. Yeah. Yeah. Here, you have freedom to choose. Yeah. Here, my computer becomes darker, so I feel probably my battery is low. Yeah. Sorry, let me quickly connect my power adapter. Otherwise, it will be shut down quickly. Yeah. All right. Yeah, I forgot to connect it. Yeah. So usually I connect it at the beginning because doing the video recording, it consumes a lot of power, and the battery usually at this warning line about 15% battery life. So I have to connect it. Yeah. Now, yeah, so let me continue. So you have freedom to choose the data structure. Yeah. All right. The data structure should be flexible to handle the dynamic data efficiently. So you see, the requirement is non-trivial. You have to do some smart design here. Okay. All right. So let's see what kind of data structure we need. Here, let me do this chart to compare different search algorithms, linear search, binary search, linear search here, binary search, index search. Here, I use a one, so I call it index search. Yeah, some people, some algorithm textbook call it index search. Actually, it is not very popular, yeah, because it has big drawback. The problem is this index search has some big drawback. So usually in the real world applications, it is rarely used, big drawback, but it has a good property. That property could be used by our new search algorithm. All right, so we'll see that. The data structure here. Array, yeah, so the first, we use array, first three, performance, bigger of n, bigger of log n, index search. What's index search? Yeah, here, let me say a few words about index search. Index, index, right? Given an array, all right. Also, in order to find a data item, the key is the array index. How about that? The key is the array index. Given array, in order to find the element, and you know the index, can you find it quickly? You just go to the right position and grab it. That's your item. That's simple. So big one O of one. Okay, yeah. One action, you will find it, how fast it is. Yeah. All right. But it has some big problem. All right, later I will point it out. It has a huge problem. So usually it's not useful. It is not useful. So that's why in the real world, almost nobody use this index search. All right. But that idea is very useful when we develop our Hessian search algorithm. We borrow this idea. The idea is very useful. Yeah. So you will see it. Yeah. All right. But we like its performance, right? Bigger of one. Extremely fast. We like this property. Yeah. It has some, positive property and a negative property. This one is a positive one. So we like to use, inherit this positive property. But there is a huge, big negative property. We want to avoid it. So that's the reason we can develop a new data structure and a new search algorithm, Hessian. Yeah, because of we have the background of this index search. Yeah. All right. Ordering, do we require data ordered, unsorted, linear search, binary? We need to sort it. Index, unsorted. Yeah. You don't need to sort, right? Give an index, sorted or unsorted, you can find the right item immediately, right? Yeah. Dynamic. So dynamic, yeah, linear search. Yeah. Yes, you can support dynamics. When you add new data, you can always apply linear search, right? Yeah. But for the binary search, when you need to maintain dynamic data, you need to always make your data sorted. Is that expensive? That's very expensive. When a new data comes in, you need to sort it every time. Not sort it every time. You need to do the insertion and make it ordered every time. Make it ordered every time. Yeah. So it is faster than sorting, but you need to do a lot of work. So it's costly. All right. Index, yeah. So, support of dynamic data. Yeah. All right. Efficient sorting. Yeah. So, sometimes because sooner or later, you may like to retrieve your data in order. Yeah. Because why we consider this last requirement, right? Last requirement. Yeah. This is useful in database applications. In many database applications, it is very useful. Yeah, so that's the reason we also consider it efficient sorting. Yeah. No. Yeah. For the linear case, the data is not ordered. In order to make it ordered, you need to do sorting. We know it is very expensive. All right. Binary, that one, yes, because you maintain the data in order already sorted. So you just, use that order directly. Yeah. No. Yeah. So here you can see this chart, we can have an overview of the existing search algorithms. Now we like to make our new search algorithm. We need a new data structure, All right. We want to make its efficiency bigger of 1 because we know for index search, that's doable, right? But index search has some big drawback. So we need to do some big improvement. Yeah. But we like to have the bigger of 1 search performance. Yeah. Unsorted, yeah, because if you want to make it sorted, that's too hard. Yeah. We cannot do it. Yeah. We cannot do it. Too hard. So make it unsorted. So then that means we do not need to maintain the order. Otherwise, we cannot make it. Okay. All right. Yes. Dynamic. Yeah. And efficient sorting, no. So now you can see we, in our mind, when we design this new search algorithm together with its data structure, so that's the properties we like it to have. Yeah. All right. Similar to index search. Yes. So we need to explore the index search a little bit, and then we will improve. We will fix that big drawback, and a new search algorithm together with a new data structure will be there. Yeah. All right. Okay. Yeah. So what's that? Yeah. Right. Using idea of the index search. Now, I already described the index search, right? Yeah. Nothing to explain. Given index of an array element and find that index, what do you need? Right? You do not need anything. Yeah. You just retrieve it directly. Yeah. So that's why you do not see this term frequently. Yeah, because too trivial, right? Too trivial. So most people do not bother to give it a name, to give this idea some official name. Yeah. So you won't see this term frequently. Yeah. Yeah. But here I feel it's simple, but its idea is so still very important. And hashing, we can borrow this idea. We know hashing is a very important search algorithm. Okay, all right. Generalize the idea of index search. All right. So let me leave this part next time. Yeah, because this story, this story is a very good story. So I do not like to, split it 2 halves. So today I talk about, in 3 minutes, the next time continue. So that will break the story. That's not good. So next time, let me just give you that whole story. All right. So let me stop right here. One thing to let you know, because several students are asking me about the project 1 grading. I just sent email to my grader, and he returned the message. He told me he will complete the grading by this weekend. Yeah. So after he sent me the grading result, sometime this weekend, I will post. Yeah. And try to let you see the result as early as possible. Yeah, just let you know that. Yeah. All right. Yeah. So that's it.